Welcome back. We are in chapter 28 on alternating current circuits. And this is section 2, circuit elements in alternating current circuits. In this section, we will look at AC behavior in resistors, capacitors, and inductors. First of all, for resistors, you can see the diagram to the right. We have an alternating current on the left and then a resistor. And so you can see the symbol for an AC generator with the wave. And the voltage is going to be the peak voltage times sine omega t. Now let's use Ohm's law to see what the current is going to be. Current is voltage over resistance. Voltage is that time-varying sine curve. So peak voltage times sine omega t divided by resistance. And let's group together peak voltage over resistance times sine omega t, and thinking about Ohm's law, that coefficient becomes the peak current. So we have that current is also a sine wave that is in phase with voltage, and its peak current times sine omega t. And here we see a graph. We have the voltage, we have the current. If they're a sine curve, assuming no phase shift, you can see they start at 0, they go up, they go down, they're in phase with each other. Their frequencies are the same, they peak at the same time. Now, let's move on to capacitors. Here is on the right, you see the circuit diagram for a capacitor connected across an AC generator. And we'll start with the basic formula that the charge on the plates, Q, is equal to the capacitance times voltage. And remember that capacitance is determined by the physical characteristics of the capacitor, the distance between them, the area. And so let's take this formula and take the time derivative. And so dq dt equals c, so capacitance doesn't change with time. We'll move that out to the left. And then we have dv dt. And so now we can see the left-hand side, dq dt, that is current, equals c times, and now we have the derivative of voltage, and remember voltage is, as you can see in the diagram, peak voltage times sine omega t. So this is the capacitor current. Now it needs to be noted that this capacitor current, it's the current to the capacitor plates. It doesn't actually go through the capacitor. So we have current equals C times the time derivative of Vp sine omega t. And let's take that derivative. We will, in taking the derivative, we'll take the omega, and that goes, we'll throw that out to the left, times Vp cosine omega t. And since cosine curve is a sine curve that's been shifted to the left by pi over 2, then I want to turn this back into a sine curve. So let's say cosine omega t is sine omega t that's been shifted to the left by pi over 2. So we'll say omega t plus pi over 2. And so here you can see in the graph a comparison when we have a capacitor hooked up to a AC generator that there is current and there is voltage. We have them both as sine curves. Here is the equation that current is omega c times peak voltage times the sine curve. And let's look at that coefficient in front of the sine term. So that is going to be the peak current because the sine term is going to, of course, vary between -1 and 1. And so when it's 1, that becomes the peak current, or that is the current right there. So the peak current is omega c times Vp. And as we look in the graph at current and voltage, you can see since the current is shifted to the left, you can see that the current leads the voltage by pi over 2, or 90 degrees. When current is at its highest, you can see in the graph here, current is at its highest, voltage is just making its way up to its highest. It's still got a quarter of a cycle left to go. Let's go back to the equation. The peak current, we'll call it I sub p, is omega c times V sub p. And this resembles Ohm's law, the idea that current is voltage divided by resistance, or if you look in the blue box, you can think of it as peak current is, and Ohm's law says current is resistance times voltage. So we've got this thing right there in parentheses that is kind of resembling resistance. Now, it's not resistance, but mathematically it kind of resembles it. Well, let's investigate that. So we have peak current is peak voltage over 1 over omega c, and we're going to call that x sub c. We're going to define x sub c as 1 over omega c. So that x sub c is sort of like resistance. We're going to call it capacitive reactance. It is measured in ohms, and it gives a relationship between the peak voltage and the current. So I say it's sort of like resistance in that if you think back to Ohm's law, it gives a relationship between peak voltage and current. And also it's measured in ohms, but we call it capacitive reactance. It's different from resistance in that, well, first of all, it's not resistance, but also there's a phase difference between voltage and current. So resistance is more current equals voltage divided by resistance. But here you have to keep in mind the peak voltage and peak current are happening at different times. Remember, they're off a quarter cycle from each other. So we have the capacitive reactance. It's 1 over omega c. So we think, how does the frequency change that? Well, as omega goes down to 0, that reactance goes to infinity, which means as omega goes down to 0, so it's no longer alternating current if the frequency is 0. In that case, nothing is changing. There's no charge moving on or off the plates, and the capacitor acts just like an open circuit. However, at a very high frequency, the capacitor has a low resistance, and I put that in quotes. It acts like a short circuit. Okay, so in this video, we've looked at alternating current with a resistor. We've looked at alternating current with a capacitor. And now we're going to look at alternating current with an inductor, such as in the diagram you see to the right here. We're going to use the loop law. So remember Kirchhoff's loop law. We're going to go around the circuit, pretty simple application of the loop law. So as we go around, it's Vp sine omega t. We're going to say plus the voltage across the inductor and bring it around, that equals 0. In chapter 27, specifically section 4 on inductance, we learned this, that the voltage of the inductor is equal to negative L times di dt. So that is the inductor's EMF. And now let's put these two equations together. I'm going to rewrite the top equation, but substitute in for E sub L, I'm going to make that negative L di dt. And while I'm at it, I'm also going to add it to both sides of the equation so as to put it off to the right. So when we do those steps, we've got peak voltage times sine omega t equals L di dt. Now, I want a relationship that involves current, not the derivative of current. So we're going to integrate both sides of this equation. And so here we have, I've put the integral signs on both sides, and here, if you follow along, I'm just doing the right-hand side. So the integral L di dt integrated with respect to time, that becomes the integral of L di. Let's get the L out to the outside because that's just a constant, and it just becomes L times I. So that's going to be our right-hand side of the equation. The left-hand side, now let's go back here. We're going to integrate peak voltage sine omega t dt, and you can go through the integration, and you get negative peak voltage over omega cosine omega t Li. All right, so there it is up top. You might have noticed if you went through the integration, what about the limits of integration? So we've set those integration constants to 0 because non-zero values would represent a direct current EMF and current that aren't in this circuit. And so we just make those 0. And so solving this for current gives, here we go, current is negative peak voltage over omega, and there's the L down in the denominator because it started up in the top equation, L times I, so we've divided both sides by L, cosine omega t, and let's turn that into a sine function. We have Vp over omega L sine omega t minus pi over 2. And the last step follows because sine alpha minus pi over 2 is negative cosine alpha for any alpha. So if you're thinking, wait a minute, I thought earlier in this video that was a plus sign. Well, yes, it was, but I've tied into it. There was a negative sign here. That negative sign got put in there, and it works. Okay, so current is Vp over omega L times sine omega t minus pi over 2. All right, so if we compare voltage, that sine curve, with current, notice that minus pi over 2, it means that for inductors, the current, as you can see in the picture, the current lags behind voltage. So when voltage is at its peak, the current is making its way up to the peak, still hasn't gotten there. It's got 90 degrees or pi over 2 to get there. Also, I want you to see peak voltage, this little bit right here, Vp over omega L, that is, we think about how this might relate to Ohm's law. So peak current is a Vp over omega L, and we're going to call that denominator, we're going to call it X sub L, just like a capacitor. Remember, we had capacitive reactance, it was X sub C. Well, now we've got a similar term, X sub L, for an inductor. And so in this case, actually, in the case with a capacitor, remember, peak current was omega C times Vp. So this is just a review of a previous slide in this video. And so we call that capacitive reactance. It was 1 over omega C. But now, with an inductor, we have peak current is peak voltage over omega L. So here we have that inductive reactance. So the inductive reactance, which again, like with a capacitor, it sort of acts like resistance. It is omega L. Now, in this case, no power is dissipated as it would be with a resistor. Energy is alternately stored and released as the magnetic field increases and decreases. So with a capacitor, energy is alternately stored and released in an electric field. With an inductor, it's stored and released in a magnetic field. The result of this, if you see that reactance is omega L, actually first let's go up to here. This is the energy stored in an inductor, that energy is 1/2 Li squared, and it's very reminiscent of energy stored in a capacitor is 1/2 CV squared. But now we have the inductive reactance, it's omega L, and let's think about what that means in terms of omega and L. If we have a high inductance, so a high L, that means there's going to be a greater opposition to a changing current. If we have a high frequency, that means there's going to be a greater opposition to a changing current as well. So let's review. You think about the different equations that we've seen and the different charts showing with a resistor, capacitor, and inductor how voltage and current compared with each other. So this is the amplitude and phase relations in circuit elements. So with alternating current, if you have a resistor, then peak current is, this is the simplest one, just peak voltage divided by resistance. and they're completely in phase with each other. If you have a capacitor with AC, then current, peak current, is peak voltage over 1 divided by omega c, or you could just say peak voltage times omega c, but current leads voltage by pi over 2, or 90 degrees. And then finally, with an inductor, peak current is peak voltage divided by omega L, and as we saw, voltage leads current by pi over 2, or 90 degrees. So here is a got it question. A capacitor and inductor are connected across separate but identical electric generators, and the same current flows in each. If the frequency of the generators is doubled, how will the currents in the two components compare? All right, so we've got our capacitor circuit, our inductor circuit, same currents, and then we're going to double the frequencies. And the choices are they'll continue to carry equal currents. The capacitor will carry twice as much current as the inductor. The inductor will carry twice as much as the capacitor, or one or the other 4 times as much. Well, let's see. Remember that for a capacitor, the current, the peak current, is related to the frequency, directly related to the frequency. And for an inductor, the peak current is inversely related to the frequency. So we think if we double both of these frequencies, both of these omegas, we double this one and we double this one, how will the currents compare? And I hope you see that the current on the capacitor is going to get doubled if frequency doubles. And yet the current on the inductor is going to get cut in half. So for the capacitor, the current is doubled. For the inductor, it gets cut in half. And so the capacitor will carry 4 times as much current as the inductor. All right, let's do an example from the book, Inductors and Capacitors, Equal Currents. It says a capacitor is connected across a 60 hertz, 120 volt, and that's root mean square, power line, and an RMS current of 200 milliamperes flows. 3 questions. Find the capacitance. What inductance connected across the same power line would result in the same current? And how would the phases of the inductor and capacitor currents compare? All right, let's write down the given information. We have frequency is 60 hertz. What's going to be useful is omega, the angular frequency. So 2 pi times frequency, well, let's call that 120 pi radians per second. The RMS current is 0.200 amperes. And since the question is asking about, well, it's giving the current, it's asking about capacitance, it's asking about an inductor, the inductance, let's use those relevant equations. So peak current is omega c times voltage peak, and RMS current, therefore, is omega c times RMS voltage. And remember, because the current RMS and peak are related by the square root of 2, so it's going to be that same relationship there. And so we can solve for the capacitance. It's RMS current over omega RMS voltage. Plug in those numbers, you get 4.421 microfarads. So that is the answer to question A, 4.421 microfarads. Question B, an inductor with the same current must have the same reactance. Okay, so reminding ourselves, for an inductor, current is voltage over omega L. For a capacitor, current is omega C times voltage. And so we're going to set those currents equal to each other because it says we want to result in the same current. So what inductance is going to do that? So we're going to set those two currents equal to each other. From the inductor equation, the current is V RMS over omega L. From the capacitor equation, its current is omega C times V RMS. And we're going to solve for the inductance. Go through the algebra, the voltage divides out, and you should get that the inductance is 1 over omega squared C. Now C is given by 4.421 microfarads. We found that in question A. Frequency, we already know that. F is 60 hertz, so omega frequency is 120 times pi. So we plug all those in, we get 1.59 henries for the inductance. And how do the phases compare? Well, remember, back to this chart, when we have a capacitor with an alternating current, the peak current, or we can say based on the sine wave equations, that current leads voltage by 90 degrees. The inductor, the voltage leads the current by 90 degrees, so we can say that the capacitor and inductor currents are 180 degrees out of phase. So as we put it all together from this section, comparing inductors and capacitors, a capacitor opposes quick changes in voltage. An inductor opposes quick changes in current. For an RC circuit, so for a resistor and a capacitor together, voltage builds up across the capacitor. For an RL circuit, current builds up in the inductor. And so as we think about an RC circuit versus an RL circuit, with an RC circuit, here we have the voltage builds up across the capacitor. And again, this is not for an alternating current. This is just for regular battery. With an RL circuit, the current builds up in the inductor. So we see a lot of similarities between an RC circuit and an RL circuit. And so when we compare inductors and capacitors, putting a lot of it together that we've seen in the last chapter and in this one, defining the relation with a capacitor, the capacitance is charge over voltage. With an inductor, the inductance is magnetic flux over current. And we're doing this a bit of a review just to see similarities and differences between the two. Defining the relationship in differential form with a capacitor, current is C times the time derivative of voltage. With an inductor, the voltage is negative inductance times the time derivative of current. Capacitor opposes changes in voltage, and inductor opposes changes in current. For energy stored, with a capacitor, it's stored in an electric field and it's 1/2 CV squared. With an inductor, the energy stored is in a magnetic field and it's 1/2 Li squared. Behavior in low frequency limit with a low frequency, and this has to do with the reactance, whether the capacitive or inductive reactance. For low frequencies, a capacitor acts like an open circuit. An inductor acts like a short circuit. In high frequencies, the capacitor acts like a short circuit, the inductor acts like an open circuit. We have the reactance, which is X sub C with a capacitor, so the capacitive reactance is 1 over omega C. The inductive reactance for an inductor is omega L. And in terms of the phase shifting, with a capacitor, the current leads voltage by 90 degrees, and with an inductor, the voltage leads current by 90 degrees. And that is the end of section 2. Have a great day.